Hi everyone, Mr. Lee here. In this video, we're going to go over vector notation, vector addition, and how to find different vectors. Alright, let's begin. So let's start off by describing what a vector is. If you remember in one of the first videos, we said that a vector is anything that has both magnitude and direction. And we described vectors and like how we can write vectors using arrows. So for example, if I have vector A versus vector, we'll call it vector A first, and vector B, we can say that vector A has a smaller magnitude than vector B, and we can tell that by the length of the arrows. And that actually comes into play. Now, one thing about vectors that I do want to start to emphasize with all of you is the direction part. Okay, so this is the arrowhead. Now, a lot of times when students draw vectors, they forget the arrowhead. But without the arrowhead, you're just simply drawing a magnitude. You're not drawing a vector, or you're drawing a scalar. So the arrowhead is actually very, very important, especially when it comes time for us to do the different kinds of math that is required with vectors. Okay, so I want to first start off with some vector addition. All right. Now, I'm not going to go too deep into vector addition and too deep into vector subtraction, but vector addition, it looks kind of like this. So if we have two vectors, right, we have vector A, and we have, let's say this is vector B. All right, so we have vector A and vector B, and if we were to add them together, A plus B, I'll do a little symbol in between, A plus B, we would get something that ends up looking like this. So the technique here is this technique called a tip to tail method. And so what that means is if we were to write out the formula, right? So A plus B is equal to, so this is what it would look like in formula notation, but up here is what we are going to use as like a tool to really visualize this. So in order to add them together, we're going to use this this idea called a tip to tail method. So I'm going to first start off by drawing vector A. So this is vector A. And then at the end of vector A, at the arrowhead, okay, at the tip of that arrowhead, I'm going to create my tail. So this is the tail of the new vector. So this is vector B. I'm going to start it where vector A ends. All right, so that's vector B. All right, now here is my A plus B. I added the two vectors together. And so our resultant, okay, we're going to go from the very, very beginning, and we're going to end at the end, right? So we're going to create another vector, and we can call that vector C. Now, the important idea here is that the arrowheads tell us in what direction we are ending up. So what this means is because our final vector, B, ended up right there at that point, our vector C has to point in that direction. Right? So this is the tip to tail method, and this method is just a way for us to draw out the vectors. All right, now what does this mean for us? Okay, so this is a good graphical representation, right, for us to be able to see it, but what does this mean in terms of numbers? So let's break that one down. If I have vector A, okay, in order to mathematically add vector A to vector B, we have to break vector A down into its components. Now, components is just a fancy way of saying what are the X, Y, and sometimes Z, okay, if we're doing in 3D, X, Y, and Z, parts of that vector. So, for example, if I take a look at vector A, and if I were to describe it, I would say vector A, according to this arrowhead, is going both up and to the right. Okay, and so right there, that descriptor tells us the components. We have a vector going up, and we have a vector going to the right. And so I will draw those vectors in. We can say that this is the rightward vector. And once again, a lot of times the students forget the arrowheads. Please don't forget the arrowheads. It really, really does help here. Okay, so we have the rightward vector, and then we have a upward vector. All right, so this and the components are, I always draw them as dotted lines just to show you that they're not the real vectors, they just make up the actual vector. So we can describe if this is our coordinate plane, meaning this is the y-axis, x-axis, negative x, negative y. We can call this, if this is angle theta, this can be a sub x, and this can be, oops, excuse me, that should be a sub y. and this one should be e sub x. Okay, and both are vectors, and we know that both are vectors because they have arrowheads and they have a very specific length. Right? Now we can also do this with vector b. So I'm going to try this with vector b as well. So we have vector b that looks something like so. Alright, so if we were to break down vector b, okay, and if I were to describe vector b, we would say that vector b is going down and to the right. So we can say that it's down and to the right. And so what that means is when we create our components, we have to create both components of going down and a component going to the right. So I'm going to do the rightward component first. Okay, and then I'm going to do the downward component. So here we have, we can describe this as b sub y, and we can describe this one as b sub x. Right, and that is my angle theta right there, whatever that theta might be. And right here are my 90-degree angles. Okay, and so technically when we are adding a plus b, all right, so technically when we are adding a plus b, what we're actually doing is we are adding the a x's together, or the x components together, and we are adding the y components together. Okay, so technically we're doing both simultaneously. And when we do that simultaneously, we get cx, and then we get cy. And so from cx and cy, what we end up with are two components of the overall c vector. So I'll show you what that means here. So let's just say that a sub x is, I'm just going to give us a number. We'll say that it's 3, and then we'll say b sub x, once again, just making up numbers. Let's say it's 5. So if I use this formula up here, a sub x plus b sub x is equal to c sub x, we can say that 3 plus 5, so 3 plus 5 will give us 8. So that means that the rightward, now this is positive 8, so the rightward component of c will be, oops, I should do that in a dotted line, excuse me. Okay, so this is c sub x. C sub x is 8. All right, now if we take a look at the y's, all right, we'll say c sub y, or excuse me, a sub y plus b sub y is equal to c sub y, and let's just give these numbers. We'll say a sub y is, we'll say it's 3, and we'll say b sub y is negative 4. Okay, now this is kind of redundant because if I look at this arrow, I know it's going down. All right, and that negative simply means that it's going down. So even though it's redundant, it's a good way of reminding yourself that we are supposed to be subtracting these magnitudes. So we have 3 minus 4 for a overall magnitude of negative 1. So c sub y would therefore be negative 1. So I'm going to just draw a tiny little vector called c sub y is equal to negative 1. And so what we get here, we get the x component and the y component of the overall resultant vector c. So that's what c is. Okay, and if you take a look at our tip to tail method, it wasn't the cleanest, but you can see that it, you know, has the general shape of our tip to tail method over here, compared to what we just came up with over here. All right, so that's what the tip to tail method is, but in numerical and mathematical form. And from there, of course, you can find the angle by using our trig identities. Okay, that's a really cool thing to do. And also, if you want to know what c is actually equal to, by the way, you just got to use Pythagorean theorem. We're going to be using that a lot, so it's definitely helpful to get used to it. So if you're wondering, the Pythagorean theorem for here will be cx squared plus cy squared is equal to just c squared. Okay, and then make sure you just square root at the end to find what vector c is equal to. Okay, so that is what it looks like in vector notation. All right. So the next thing I want to do is, just in case it's been a couple years since you took trig, I want to go over how to use Sohcahtoa in order to come up with your x components and your y components. All right. So this is, I'm going to label it trig. All right. So just so you know, we got oh my gosh, Sohcahtoa and Sohcahtoa. And as a reminder, so the S is sine, the O stands for opposite, and H of course is hypotenuse. Ka is cosine, adjacent, hypotenuse. Toa is tangent, opposite, and then adjacent. Okay, so we got Sohcahtoa, and you know what? Let me highlight that to make it a little bit cleaner. There we go. All right. Now, whenever you're given a vector and you're expected to break it down, you got to use Sohcahtoa. Now, I know a lot of students like to kind of take a shortcut with this and try to just memorize, you know, when to use sine, when to use cosine. But trust me when I say it's best not to memorize it and just to really think it out. Okay, so let's say that we have this component or this vector. We'll call this vector A. Okay, and we have here our 90-degree angle, and they give us our theta right there. So if I were to identify these parts of the triangle, I would say that right here is my hypotenuse, okay? And this y-axis here, this is my opposite side. How do I know it's my opposite side? Well, I take a look at where my angle is, okay? So my angle is here, and I see that this side of the triangle is opposite. This side of the triangle is opposite of that angle. And we can say, therefore, that this a sub y, okay, will be opposite of that angle. All right, now what about a sub x? What about a sub x? How can we describe a sub x? Well, once again, you just got to take a look at your angle. So here's my angle, and here's the side of my triangle. So we can see that the angle and the side of my triangle, they're touching each other. So that means that this is adjacent. Okay, so a sub y is opposite, a sub x in this scenario would be adjacent. Now it can always change, and I'll show you an example next of where we can get that. Now, if I were to find a sub y and a sub x, we have to use the trig identities. So we see here that opposite is a sub y, and so we're going to use our sine identities. So we can say that sine of theta is equal to opposite over the hypotenuse. Okay, that's where the SO and the H comes from. And we can substitute in the values that we know. So opposite for us, we call that a sub y, and our hypotenuse will just be a. So a sub y is equal to a sine theta. All right, and we could use the same idea here for the a sub x. A sub x is adjacent, therefore we have to use the cosine. Cosine of theta is equal to the adjacent side divided by the hypotenuse. Okay, and we can substitute in the different values that we know. We know the adjacent side is a sub x and the hypotenuse is a. And therefore, we can say that a sub x is equal to a cosine theta. Okay, and that is if and only if the angle is right there. So let's say we have a different triangle and we need to figure out the vectors for that one. So let's say we have, I don't know, a triangle, a vector like this. All right, so we have a vector like that, and our components look like so. All right, and we say that this is our theta. So instead of memorizing a sub y will always be the sine, and instead of memorizing that a sub x will always be the cosine, this is what I mean by it's always best to just think it through. If my angle is right there, okay, and we say that this is a sub y, and we say that this is a sub x, if my angle is right there, we have to be able to identify that a sub x would be opposite, and that our a sub y, because it's touching that angle, this would be our adjacent. So in this scenario here, a sub x would be the hypotenuse, so we're going to call this a, would be a, opposite will be sine of theta, and because a sub y is adjacent, we can say that this will be the a cosine of theta. Very much opposite of what we just discovered over here. Okay, in fact, it's the exact opposite here. But the reason why I want to show you that is because I want to show you the technique behind it. All right, so the last thing I want to show you is the hat notation. All right, so we know that our coordinate plane, okay, this is the y-axis, this is the x-axis, and if we're in 3D, this is considered to be a z-axis. We're going into, okay, the the negative zone right there, the negative 3D zone, that would be negative z, right? And so we are going to be using this notation called the hat notation, and it follows the letters I, J, and K. All right, and so this is just a good way for us to describe that we are using a vector. So instead of saying the x-axis, if we have a vector along the x-axis, we can say that it has, we can put a notation called I hat. So it's kind of a little caret on top of it to describe this as a vector. So instead of saying that it's along the y-axis, and for describing a vector, we can call it a j hat. And instead of saying that it's along the z-axis, we can call it the k hat. And of course, if it's along the negative y, we can just call it the negative j hat, and so on and so forth. But the reason why I wanted to show you I, j, k is because it follows in the alphabetic order x, y, z. Right? So if you're ever wondering what direction is I, well, it's x because it's the first one. Okay. If you're wondering, what about k, it's z because it's the last one. All right. So with that out of the way, I want to show you one last thing on how we can write the different notations. All right. So if we are given a vector, now personally, I think this way is solving it a lot easier, but it just takes a little bit getting used to. If we have a vector called a, right, we can say that a, I'm going to do 2D first, has two vectors that make it up. Right. So we have a vector called, or we have a magnitude of a sub x that is along the I hat vector axis, and we also have a sub y that is along the j hat axis. So what this means for us here is that if we have a vector called a, okay, and we are along the coordinate plane, okay, the xyz coordinate plane, or excuse me, in this case it'll be just the xy coordinate plane, and we were to break this down like we did earlier, right? We were to break it down like we did earlier, where this is a y and this is a x. We can say that a y is comprised of, excuse me, we can say that vector a is comprised of a y and a x, right? And that's what we wrote over here. Vector a is comprised of a y and a x added up together. Now, if we're dealing with 3D stuff, we can also say that it's ax I hat plus ay j hat plus az, ooh, k hat. Okay, if we're doing 3D stuff, right? And the only other thing that I want to mention here is be careful of the positive and negatives when you're adding things up. So for example, if you have a vector that looks like this, right, we'll call this b. Technically here we have a negative by or a negative j hat, and we have a negative b sub x here, okay, because it's going down and to the left. So this is why arrowheads really do help. All right, so you might be wondering, Mr. Lee, why would we want to use this hat method when we have all these other ways of writing it? Okay, why can't we just go straight from what we know here? Well, you can, and in fact, it's the same exact thing. It's just a different way of looking at it, and personally, I think it does look a little bit cleaner. Okay, so for example, if you are given the vector notation, okay, of a hat is equal to, let's say, I don't know, 7 I hat plus 8 j hat. Okay, so we are doing with what we have over here, and we have vector b is equal to negative 12 I hat plus negative, I don't know, 14 j hat, right? If we were to add a plus b together, what would c be, right? So that's our question. And so in order to do it, we can just state that c is equal to, so we gotta get the a hats. We get, what's it? 7i minus 12i, okay, plus 8j minus 14j. Okay, and we can say that C is comprised of the two vectors known as negative 5 I hat and what is this? 6? Yeah, negative 6 j hat. Okay, and so these are like our coordinates. We can see that if we were to add these two together, our vector would look like it's going down and to the left. Woo. So this -5 means that it's going down -5, and this -6 means that it's going to the left of -6, and so our resultant would look something like this. C would look something like that. Okay. So this hat method is just another way of writing things out. You can find what these magnitudes are, right? You can find what the 7s and the 8s and the 12s and the 14s are if you're given the angle, and we just got to use our trig identity. But this is just another way of representing the information that we know with a different kind of notation. Okay, so we can use the sines and the cosines to figure out the magnitudes. Yeah, so with that, let's just do a quick recap. The trig identities there help us not only to find the magnitudes, but the drawings also help us find the directions. Okay, we went over Sohcahtoa, and we went over how the angle actually determines if it's sine or cosine. All right, and it's just not a downright formula. We went over how we can use the hat notation. Okay, remember, it's just a different way of writing vectors. It's just another way of representing information. And we can use the hat notation to do vector math as well. Okay, and we did a quick little example there. And at the very beginning, we went over how we can use the tip-to-tail method. Okay, and the tip-to-tail method is just a very basic method, and from there we saw how the tip-to-tail method, we can break it down mathematically, and how we can apply numbers. Remember, the tip-to-tail method is just a way of drawing out the vector addition. Okay, but everything else is the way to actually calculate and compute the math using vectors. All right, I'll see you next time. Bye-bye.